Something you might encounter is the concept of confusion matrices. So let's dive into what those are all about. What's a confusion matrix for? Well, the thing is, sometimes accuracy doesn't tell the whole story, and a confusion matrix can help you understand the more nuanced results of your model. For example, a test for a rare disease could be 99.9% accurate by just guessing no all the time, by saying you don't have it. A model that does that would look on paper to have very high accuracy, but in reality, it's worse than useless, right? So you need to understand with a case like this how important a true positive or true negative is, how important a false positive or a false negative is to what you're trying to accomplish, and to be able to measure how good your model is at each one of those cases. And a confusion matrix is just a way to illustrate those nuances in the accuracy of your model. One might look like this. This is a general format of it. So imagine that we have a binary situation where we're just predicting yes or no, like I have this disease or I don't have this disease, or I test positive for this drug or I don't test positive for this drug. This image has a cat in it, or this image does not have a cat in it. This is the format of what it would look like. So you see that on the rows we have predicted values, and in the columns we have actual values. So go through it. If we predicted something is true, and it really is, then that's a true positive. If we predicted yes, but it's actually no, actually negative, that would be a false positive. If we predicted no, but it's actually yes, then that's a false negative. And if we predicted no and it's actually no, that's a true negative. I mean, it gets a little confusing, but if you think through it, this all makes sense, right? So in an actual confusion matrix, these cells would contain actual numbers of how often your model actually did that on its testing data set. So keep in mind, too, that you have to pay attention to the labels. There's no real convention to how this is ordered. Sometimes you'll see predictions up here and actual values over here. Don't just jump in assuming that a given confusion matrix is of a certain format. Pay attention to how it's labeled and make sure you understand what it's telling you before you draw conclusions from it. Something else worth noting here is that you typically want to have most of your values here and here, right? So the diagonal here of your confusion matrix is where most of your results should be. This is where accuracy lives, right? So this is where I have a true positive. This is where I have a true negative. You want those to be, nice big numbers, and the false negatives and false positives to be, comparably low numbers, hopefully, right? So an accurate model would have high numbers along this diagonal value here. Let's plug in some actual numbers to see what that might look like. So say I have a machine learning model that's trying to figure out if an image contains a picture of a cat or not. If we predicted that it had a cat and it really did have a cat, that happened 50 times in my test set. But sometimes I predicted it was a cat, but it wasn't a cat. It was a dog or a fish or something. That happened 5 times. If I predicted that wasn't a cat, but it really was a cat, that happened 10 times in this example. And if I said it was not a cat and it really was not a cat, that happened 100 times in this case. So that's just how you interpret a confusion matrix. And we'll talk about how to make metrics off of this data that are more useful for analysis shortly. Sometimes you'll see confusion matrices in a different format where we actually add things up on each row and column as well. So that's something you might see once in a while. All that is adding up, how many actual no's we have, how many actual yeses we have, how many predicted no's we have, and how many predicted yeses we have in total. So just so you have seen that format before, that's what that looks like. The inner part of it, though, is just the same confusion matrix that we looked at before. And again, remember, things can be flipped as far as where the predicted values and the actual values are. So make sure you pay attention to the labels on these things. And, what can I say? Confusion matrices can be confusing. Sometimes you'll see them in this sort of a format too. So maybe we have a multi-classification model here too. Imagine that we have a handwriting recognition system that's trying to identify somebody writing the values 0 through 9. So a more complicated confusion matrix might look like this, where instead of just yes-no answers, we actually have multiple classifications. But it works the same way. So here we have predicted labels on this axis and true labels on this axis. So we're saying that if I predicted something was a 5 and it really was a 5, well, that shade of blue corresponds to some number here. So 2 things that are different in this example. First of all, we have more than yes-no options here. We have multiple classifications, so our confusion matrix is larger. Let's dive into another example there just to drive that home. So sometimes I predicted it was a 1, but it was really an 8. That has sort of a lighter blue there. Maybe that happened, 20 or so times in this example. And we're also using what's called a heat map. So instead of just displaying numbers in these individual cells, we're mapping those numbers to columns where the darkness of that color corresponds to how high of a number it is. You would expect to see sort of a dark line going down the diagonal here, representing a good accuracy on true positives and true negatives. And some sparser, lighter colors outside here, ideally. but that color will map to an actual value, and it just makes it easy to visualize how your confusion matrix is laid out. All right, makes sense, guys? That's what a confusion matrix is all about. It can be a little bit confusing, but just stare at these examples a little bit, and it should make sense to you.